be where there's a huge asteroid coming towards Earth.
Armageddon.
Yeah.
Dang, nice.
That was pretty quick. Okay, so what about this? Bike rider approaches a hill. We started talking about this,
Soren.
and we kind of, yeah, Soren, exactly. And we kind of ran out of time at the end. All right, so this is where we got to talk about mechanical energy just a little bit. So mechanical energy is the combination of kinetic energy and gravitational potential energy, right? Gravitational potential energy, and that's what this stands for.
¿Qué es eso?
Yeah, yours first, mine yours.
Who just is this rubber?
Get it in, okay? So gravitational potential energy, U, is just mgh, right? But you got to be a little bit careful with this. What is the h? The h is just the, if this is our hill that we're traveling up, height is just the distance above the place where you're going to say that gravitational potential energy is equal to 0. Totally arbitrary, right? So all that's really important to us here is just that gravitational potential energy is just going to be changing as you change your elevation above or below that place, right, Lincoln? Okay, good. So what we'll typically want to do then is we'll typically want to make gravitational potential energy equal 0 at a convenient place. Like here, for example, if the person's riding along this flat level road, before they go up the hill, that's probably where we're going to say, let's let h equal 0 there. That's where the gravitational potential energy is going to equal 0. But we don't have to. We could arbitrarily say it's 1 billion. And then when it goes up the hill, it's going to be a little more than 1 billion, right? So it's, and why is that? That wouldn't change the answer, because then the total mechanical energy would just be, 1 billion and something else afterwards, and 1 billion and something before it goes up the hill, because now that little bit of extra would be kinetic instead of potential. But why would we do that, right? Instead, we would say, well, let's just make the gravitational potential energy 0 there, because it's easy to account for it, right? When he goes up the hill, the kinetic energy that he loses is going to be converted into potential energy as long as friction isn't acting, right? If friction's acting, then we're actually going to lose some mechanical energy, okay? So mechanical energy is conserved if there's no other forces acting that are robbing us of energy, right? Here's where we got to just, and I want to just mention this word. I'll talk about it very briefly. If you go on and study physics in college, you'll talk more about this, but a conservative force is any force, and we talked about this in class, but in the spring, I can't remember who was here, probably not everybody. A conservative force is any force that is independent of the path you take to get from A to B, right? And so gravity is that, isn't it? If you were going to go from, like if I'm going to, the work that's done in going from A to B is independent of path. If I'm going to take this thing and set it on this shelf up here, 1 meter higher, it doesn't matter if I take that kind of a route, or if I put it straight up there, or if I walk this way and then go like, it doesn't make any difference, right? The work that I've done to put this object on the shelf only depends on how far it's moved vertically from its starting position, right? If I pick it up like so and then put it down on the shelf, yes, I've done some extra work in lifting it clear up here, but then gravity does that work on the way back down and gives it back to me, in a sense. You get it? So gravity, the work I do in going from one point to another is irrelevant, or is always the same, regardless of the path I take, as far as gravity is concerned. Right? Now, friction doesn't work that way. Right? Classic example here would be if I'm going to push this thing around on the desk, there's some friction that always opposes me, right? So if I want to go from there to there, if I push in a straight line, I'm doing a certain amount of work against friction, right? let's say I'm pushing with 1 Newton of force as I slide this thing along the desk to overcome friction. If I'm moving at a constant speed, let's just say hypothetically. Well, if I move this thing, pretend that's 1 meter. If I move that 1 meter against friction, then I've done 1 joule of work to move it from point A to point B, right? But now what if I take a path that requires me to push it through 2 meters? Well, now I had to do 1 Newton of work, I applied 1 Newton of force through 2 meters, right? So that took me 2 joules. Different, right? I started here and ended here both times, but different path lengths required me to do different amounts of work, right? So friction is a classic example of what we would call a non-conservative force, right? So there's another kind of more sophisticated way of talking about the work energy theorem, and this is it. We would say that the work due to non-conservative forces equals the change in mechanical energy. Okay, that's not in our textbook, but that's a really kind of cool way of thinking about it, right? Any change in the combination of kinetic and potential energy can only be caused by a non-conservative force, right? Take the example of the bike moving up the hill, right? If there's a perfectly frictionless bearings in the bike, let's say, right? When this guy's moving along the ground down here, if he's got 1,000 joules of kinetic energy as he's cruising along on the ground, well then as he moves up the hill, he's gonna slow down, but when he gets to the highest point, what do they call it, the high point on the hill, before he'd start to roll back, if he puts on the brakes or at that exact time and stops and prevents himself from rolling backwards, then at that point, how much potential energy would he have? That much, 1,000 joules, right? See what I'm saying? So mechanical energy was conserved, right? It was all kinetic down here, it was all potential up here. Somewhere in the middle, it's gonna be half 50-50, right? But the sum of kinetic and potential would be the same the whole time. Now, in reality, that's rarely ever gonna happen because there is gonna be some internal friction. And when he gets to the top, he's probably going to, maybe, let's just say hypothetically that instead of 1,000, he's only got 900 joules of gravitational potential energy, okay? So then he lost a little bit, right? Well, you can tell me now, what was the work due to gravity? How much work was done by gravity? Negative 100, right? Does that make sense? Because that's how we lost some mechanical energy. The only way mechanical energy is lost from the system is when a non-conservative force does some work, okay? What if we could do it the other way too? What if on the way up, I cheated and I pushed him a little bit, so we went a little bit higher, right? Let's say that now instead of the 1,000 joules of kinetic energy that he started with, he's got 1,050 joules of potential energy at the end. How do you account for that? Well, because I gave him a push, right? That was a non-conservative force. Okay, make sense? All right, so, yeah, so you guys can do this then, right? So all you're gonna have to do here, the part that's a little bit new, is we're just gonna set the gravitational potential energy equal to 0 at the bottom. That's the convenient place to do it. And then that means that the H is just equal to, when we calculate gravitational potential energy, we're setting H equal to 0 there, right? And so this distance, we would now call H, right at the top of the hill, right? At the top, his kinetic energy is 0, and his potential energy is mgh. At the bottom of the hill, his kinetic potential, or his kinetic energy is 1/2 mv squared, and his potential energy, I guess just call that U, I call it P, is 0, right? Anything that's lost is lost because of a non-conservative force, in this case it's friction. Okay? Make sense? The friction wouldn't even have to all be the same kind of friction. We could just put it under the umbrella of friction.
What are the two symbols by the
The subscription.
NC for non-conservative. Yeah. Okay, so this, and once again, that's not in the book, but it's kind of that. You don't have to have that, honestly, you really don't. But it's just, it simplifies the whole way of thinking about it a little bit. Okay? We good? All right, work. We'll talk about collisions on Monday, and that's our last topic. Elastic collisions. And we're only gonna do elastic collisions in one dimension. I just want you to have some exposure to how they work. And
So we
that's
get
good enough.
extra credit if we can go to 3 dimensions.
You can do it in 4 dimensions.
The extra karma credit, yes you do.
Karma credit doesn't count worth credit.
No, it does. It does.
Karma credit doesn't count worth credit.
That's-
You can use it for rhetorical devices.
Yeah.